a couple of things before we start with, for those of you who came in at the last moment, this first table here with Wes, Sarah, and Nathan is going to do one of the homework problems for us. Hopefully you're now kind of in the groove. There's only one more kind of assignment that you haven't done. So just to review the assignments that you have the reading quizzes. And thanks to Wesley, I figured out what the problem is. I don't have access to the page you guys need to go to for the reading quizzes. So the link I was putting has a /t at the end for teacher, apparently. And that's what was causing the problems. So I've fixed the URL. When I click it, it just redirects to the one that I gave you. But it took care of the problem as far as we could see. So I'm glad we've got that straightened out. I think we've got it straightened out. So you have the reading quizzes, which are due 5 minutes before class. And that's on the OpenStax tutor. And then you have the homework that is due not at class time, but you do go over it. One problem one group has to do in class. The reason it's not due until later is so you can revise things. You have a chance to talk to me to learn from the group that does it. And that's on Expert TA, which apparently have changed their preferred way of writing it. So there's a space now. And then we had the lab reports. Everyone turned in their lab reports. They're turned in on Moodle. And then I grade on Gradescope, and I accidentally had it send out notifications to all of you this morning about me adding you to the roster on Gradescope. You don't have to interact with anything on Gradescope, so I meant to unclick that for sending you, but you can look there. Anything else? Oh, yes. The thing that you haven't done yet is the pre-lab quiz, which will be again on Moodle, due by 5 minutes before lab time, so due by 1:55 p.m. on Tuesdays. Question, DJ?
I've noticed on Moodle that there's a submission spot for homework.
It's not actually. That's there for a reminder.
Okay.
I'm going to put scores with that, but you don't submit them.
Okay, I just want to make sure I wasn't missing out on things.
Okay, good question. Okay, so everybody up to date on what those assignments are? I mean, everybody did them the first time, but you want to make sure that people are, oh, yeah, I got to do that again and again and again and again. Because the first two things are every class period you have an assignment. The second two things are once a week. What is not on this list? The what? Oh, the scrapbook. Good call, the scrapbook. It's new. I forgot it. The scrapbook is due, well, a total of 5 times for just before, I think, each exam, right? And then the 5th one at the end of the semester. Okay, so there's the scrapbook. I'm looking for one that's not required because I've had more than one student ask me about it. Yeah, the supplemental homeworks are absolutely not required. Those are just for your fun. And I mean, you guys may not be nerds like me, but still remember back when I was like in 1st grade, I had this 4th grade math workbook. And for fun, I was working those math problems because, it's fun stuff. One student agrees with me. I like that guy. Certainly it was you. Okay, a reminder of what we've done. We've looked at units. One of your homework problems was on that. We've dealt with then the kinematic equations a little bit. We talked about position versus displacement, speed versus velocity. Today we're going to look at significant figures and kinematic equations. With the homework, there was one question that dealt with significant figures, and I decided I would go ahead and leave that counting. But there was one that dealt with polar coordinates, which is super important for this class. And the homework site said it was from section 2.2. And Mira contacted me and said, I don't see this. And that's because it's in section 3.3 of the textbook. And so that problem will not count toward your homework grade. So only the other 4 problems will count toward your homework grade. I left it there because it is good practice and it will remind you of things, but I'm not counting it because I don't want people to have done it wrong and say, oh, now I'm in trouble. All right. Announcement. PASS tutoring is available. What in the world is PASS, you say? PASS is whatever it says up there. Peer assisted study sessions. A lady named Ashley Beck Orcutt, she's a nursing student, is going to be, she won't be able to come to class, but she'll be watching each one of the lectures on YouTube. You guys know you can watch these on YouTube, right? It's exciting stuff, the most riveting videos on YouTube, I believe. If you don't know how to get there, just go to the Moodle webpage, because Moodle is where I do almost everything. And I'm going to change to student view because it's just a lot maybe I'm going to. It's just a lot easier to view things than it is with the teacher view. So we have here lecture materials, and if you click on lecture 151 lectures, that will take you to YouTube for a playlist that has all the lectures for the class so far. And if you look in that channel, you can see all the lectures from last year and the year before as well. There's also some tutorial problems that I've worked out and explained how I work it there. I need to put links here so you can go straight to the tutorials instead of having to go find them. So you have that available to you. Research says that it actually hurts students because they start to think, oh, I don't have to pay attention in class. But as long as you're paying attention in class and use it as a supplement, then it's okay. So she's going to be listening to the lectures on YouTube, and then she's going to have 2 1-hour tutoring sessions. And so we have to decide when we're going to have those sessions. Her times available are Monday evening, Tuesday evening, Wednesday afternoon, evening, and Thursday afternoon, evening. So there is a poll going back to Moodle again, going back and forth a lot. There is a poll on Moodle, and I put it up here near the top. Time preference for PASS tutoring. Please take this before 6 p.m. tonight to express your preference. So what you have there is all of the different times in 1-hour increments, and put preferred if that's the time you would like, can attend if you could attend but it's not your preferred, or cannot attend. And then based on the results of this, we'll choose 2 1-hour time slots on different days. They're not going to be 2 1-hour slots on the same day. That she will be here to do tutoring with you. So please do that. We want to serve you as well as we can. So you just, you check for each one. Can attend. Okay, I missed again. Yeah, just for each one, select your options. I, of course, will not be submitting this. And now we're ready to go to our group. So the 3 of you, come on up. The homework problem that you're going to do for everyone is homework problem 2. I'll go sit at their table. And if you guys need help, ask rather than just, say, we can't do it.
So all of these questions?
Yeah.
Cool. Okay. What can I look at? How do I?
How do we click it?
No, you can't. So you just answer.
Okay.
So, and you write on there, whatever you need to write.
Oh, okay. Change in T is just seconds.
Okay, why is changing to just seconds?
Because the SI unit for time is seconds, and if your final time minus initial time, the units will still be seconds.
Bueno.
Which of the following?
So write that down.
Oh,
You
sorry.
use the stylus there, right? That's,
Oh, that's tiny. Which of the following units will have units of meter?
Uh-oh. Okay, skip that one because it says which of the following.
Okay.
Can't do that
All
one.
that
right,
apply.
dude?
For the next one.
Well, just write it on the screen.
Oh, okay, cool.
That way everybody can see your work.
For C,
So that's meter squared over second squared.
yep, so V squared is equal to meter squared over second squared, and 2AR is equal to 2 times per second squared times meters. And so it's also meter squared per second squared.
So yes.
Now, when it's, it's set up there, use dimensional analysis. I never use that word, right? The textbook does, but I didn't. Dimensional analysis means essentially ignore all the numbers and just do the units.
Okay.
So the two we're ignoring, so we just have, like she said, meters per
So-
second squared, meters per second squared.
You guys want to do the next one? You want to keep going?
It's a team. We don't care how you divvy it up.
Okay. Part D, MA is equal to kilograms times meters
over second squared.
second squared. And can I write below? Does it matter? I write bigger than these spaces. And then mass volume is equal to kilograms times meters squared.
Second squared.
I just clicked on the thing. Over second squared.
Divided by 2.
Divided by 2, but that doesn't matter. And so that is D, and it's not consistent.
Correct.
And then E, which of the following has units of kilograms, meters?
Okay, can't do it because it's following again.
Okay. The units of P, which is equal to kilograms times meters over seconds. And next one, F equals MA, which is equal to kilograms meters per
over
second
second
squared.
squared.
You actually already did that one. I didn't even notice that they were redundant.
Okay. And given the formula, what are the units of E? So I'm
I'm also already done that one.
cool.
Okay, perfect.
Sorry.
Cool.
My bad choice.
So
Sorry.
that's how that goes. It's always good to have it go perfectly. You have a question, Emily?
When we do this, are we allowed to have notes up?
Absolutely. Yes. And the goal is that your homework group will have gotten together before class time and tried to do all the homework problems so that you're as prepared as you can be. And then you have the time after class if you need to make any changes, whether it was your group or somebody else that did the explaining, or whether anyone asks homework questions. So does anyone have any other homework questions before we go on?
I have another question.
Yes.
So if we get stuck in a problem, you're saying not, if we do our homework ahead of time, to not do it and wait until we possibly will do it and go back to
Yeah. If you get stuck, don't say, well, I'm going to turn something and hope for the best. And you can always contact me. My office hours aren't posted out there yet, but they're in the syllabus. You can email me, come visit me. If I'm in my office, even if it's not office hours, I usually have the door open, which means come on in. Yes.
I was trying
Lydia.
to submit that poll, and it kept pulling up an error. It won't allow me to submit. So I don't know if I submitted it twice, but it says there's an error writing to the database.
Yeah.
So just for your heads up.
Oh, no. Thank you. I will, I put in a script there to make it so it doesn't have an extra click. That could be the problem. I don't know. I'll take out the script and see. Yeah. Thank you for letting me know.
Yep, no problem.
Okay. Back to lecturing. Yeah. Oh, hey, that's not where I said to go. I said to go there. There we go. So we're going to continue with kinematics, but first I want to talk about significant digits, significant figures. I use the two terms interchangeably, even though they're not. So please forgive my misuse of the language. So with significant digits, we have a number of rules of what makes a digit significant or not. The first rule is all non-zero digits are significant. That means they're meaningful. They carry information. All 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and 9s carry information in a number. But we have more rules besides that. Any zero that is between two significant digits is also significant. So if I have, for instance, the number 101, both of the 1s are significant because they're not 0. And the 0 is significant because it's between two numbers that are significant. Trailing zeros after a decimal point are significant. Now let me write an example of trailing zeros after the decimal point. If I have the zeros that are trailing are the ones that come after a significant digit. And so we have the number that's not a 0 is the 3. The zeros after that 3 are significant. So in this number, this rule says that those digits are all significant. Next rule is the leading zeros after a decimal point are not significant. So that means the 0.00 are not significant. So this number has only 3 significant digits in it. And finally, trailing zeros on a number without a decimal point are not significant. They're placeholders. So if I have 100, the 1 is significant. The next 2 zeros are placeholders. Now, this last rule is ambiguous. It's actually, they could be significant or they could be placeholders. And so I saw somebody in their lab guide doing this. The way to indicate if it's significant, a number before the decimal that's significant, is to put a bar over it. If I put a bar over that, it means that 0 is significant. And so it would have 2 significant digits. If I put a bar over this, how many significant digits do I have? 3. Why not just 2? The rule that a 0 between significant digits is significant means that the 0 before the 0 with the bar over is also significant. So, and there's lots of things we can do for practice. Take a number like 0.450. How many significant digits does that have? Okay, it's 7. Every single one of them is significant. The trailing 0 is after decimal, so that makes it significant. This 0 here is significant because there are significant digits to the right of it. One more thing that I did not say. If I had 1, 2, 3, 0 with a decimal point, that decimal point is a way of saying that all the numbers to the left of it, unless it's all zeros to the left of it, is significant. I mean, if you write 0, 0, 0 point, well, that doesn't make any of those zeros significant. But if they are, if there's a 0 there, it makes it significant. So when we have, there was a, I think it was one of your homework problems. It had a number like 140 times, 1756. And you have how many significant digits do you have in your answer? For this homework assignment, if it's ambiguous, assume it's not significant, right? Because 140 could be 2, could be 3. Assume it's not significant if it's ambiguous for this homework assignment. What's the point of significant digits, by the way? I've gone through all these rules. What's the point? Okay, it's to note precision. What we talked about in lab. The reason in lab we had those formulas for actually calculating precision, which we didn't do those parts of the lab, is to show you how it's really done. And it takes a fair calculation for each calculation to see how many of those digits are significant. The significant digit process, the whole rules and mechanism, is there so that we can keep rough track of the precision without having to do calculations. So it's a time saver. Now, the rules for addition and subtraction. What I have found, my experience, is that most students don't know the rules for adding and subtracting with significant digits. They know the multiplication, division, and don't know the addition, subtraction. So this is the rule. The greatest of the least significant digits of the starting numbers is the least significant digit of the answer. Probably makes no sense to you. Am I correct? Does to some. Good. Well, here's the easy way to do addition, subtraction. Put it like you did in grade school where you have them in columns. So if I have 14.75 plus 360, and I want the answer, first thing I'll do is just do the addition. Okay? But that's not my answer because I haven't paid attention to significant digits. So now to pay attention to significant digits, I say which is the least significant digit, that is the smallest digit that is significant in each of my numbers. So that's the wrong one. Crud. I swear I clicked on the pin. I'm going to change the color. You guys wouldn't believe in my astronomy class yesterday, this stuff didn't work. It worked here, it didn't work there, I don't know. So what digit, just say the number, is the least significant one, the smallest significant digit in the 14.75? Number is in the 1, the 4, the 7, or the 5. I'm like, I don't see the 2. Clearly, we didn't communicate effectively there. So which number, the 1, the 4, the 7, or the 5? Is the least significant, the smallest significant digit. Okay, what Myra said is correct, the 5. Some people might say, well, 1 is a smaller number than 5. We're not talking about how big the number, we're talking about its place in the number. So the 5 is in the 100th place. So this is the least significant digit in that number. What about in 360? The 6. And so the rule is I take the greater of those two. Well, which is bigger, the tens place or the 100ths? Not a hard question, right? The answer is the tens. And so that means my answer is going to be significant to that level. So the answer to correct significant digits here is 370. Now, when you're doing homework on that homework site, don't pay attention to significant digits there. You need to know them. Expert TA doesn't. So an expert TA, always put 4 digits. Just always do that. The way it works is it takes the correct answer and then it gives you plus or minus like 2%. And it'll be correct if you do plus or minus 2% of the correct answer and pays no attention to significant digits. But if you use proper significant digits sometimes, then having the proper number, the correct number to proper significant digits will be more than 2% away from the calculated value, and it'll mark you wrong. So that's why you just always use 4 digits, then you won't have that problem. It is regrettable. So does that make sense, the rule for addition here? And subtraction is exactly the same rule. I'm going to throw in one more thing. If I had to round 375 to 2 digits, that's to tens, what would it be? How do you round 375 to the tens?
Depends on what system you're using.
We're going to use the scientific one, but it doesn't actually. This one here is the one that everyone's going to get right. It would go to 380. What if it was 385? It's still 380. The rule is if it's exactly 5 on that digit that you're rounding from, then you go to the even number. The reason for that is to avoid a bias in your rounding. Because 5 is halfway between. If you always go up with it, you're biasing to a higher average. No one's going to ever test you on that in this class, at least. No one is me anyway. I will never test you in this class on it. But it's kind of useful to know that rounding is a little more complicated than what I learned in first grade or second grade or wherever it was. When I was in grad school, we had a teacher say, and you learned this in high school calculus, and we're all, sure we did, because we all took calculus in high school, right? No. Okay, multiplication division. This is the one that most people are very comfortable with. Multiplication division, you count the number of significant digits in each number, and the one with the smallest number is the number of significant digits in the answer. So if I had 14.75 times 360, okay, I can't do that in my head. Sue me. How many significant digits do I have in the first number? 4. How many do I have in the second number? Good job. 4 there, 2 there. Which one's smaller? 2. And so my answer is going to have 2 significant digits. Now I saw James got the calculator. What is the full number you get?
5,310.
So 5,310. Come on, erase. And then 2 significant digits, so that becomes 5,300. And so that's the one that most people have a handle on. And a lot of people will try to use that rule and apply it to addition and subtraction, but it's a different rule. So when is this going to come up? It will come up, well, in homework problems like today, as well as you'll probably have one test question on the first test and maybe one on the final exam that makes sure you understand how significant figures work. Other than that, we're just going to take it for granted that you can do it. Me again. I don't know why I became, we. All right, velocity and acceleration. We learned last class period about the difference in velocity and speed. What is the difference in velocity and speed? Direction. Velocity is a vector and it has direction with it. Speed doesn't have direction. It's just a magnitude, how big the number is. Oh, by the way, Ryan, I assume you copied and pasted that email. Is that correct? Or did you type it?
No, I typed.
You typed it. Okay. Well, then if you missed something in the typing, I can't answer correctly. I was going to look it up.
Oh, so the second one with the problem that I had with the actual question.
Yeah.
I copied and pasted the question.
Okay, you did. Okay. So what I saw there was a question. It said that you have a train that starts at this speed and it had 3 significant digits, and it's slowing down, and the student gets this answer, and it have 4 significant digits, and then it says, what's your sign that they might have made a mistake? Select all that apply, right? The correct answer on that was they had 4 significant digits in their answer and only 3 in the number they started with. You can't go up in significant digits because you're dividing that. And so that was what the answer should have been, I believe. I didn't look at it to, see if what they had. Okay, so I just remember now. I forgot to respond to you. So we learned this first equation that said that This is written without vector signs. So if I read this correctly, it says speed is change in position over change in time. If I add vector signs, only on the numerator, time is not a vector. Time doesn't have direction, just goes one direction up. Then its velocity is equal to displacement over time. Changes the words a little bit here. What does delta mean? Change in, which is always blank minus blank. The final value minus the initial value. So we've already dealt with that equation. We can take this equation and just solve it for the change in position. And so if you know something's speed, you can find the change in position. Now here's something I haven't been careful with. This equation is correct as long as the speed is the, oh, my hand hit a key, is the average speed. The change in the position is the average speed over the change in time. And likewise, it's the average speed is the change in position over change in time. Instantaneous speed, right, when you're driving down the road, your speedometer doesn't say your average speed for the last minute has been this. It says what your speed is right now, the instantaneous speed. The difference in those is the instantaneous speed is shrinking down the time over which it's calculating the average velocity to a negligible time. The term we use is infinitesimal, on the order of 1 over infinity for the time. That's where you get instantaneous speed. The acceleration is defined like velocity. That is, the acceleration is the change in velocity over change in time. And this one here actually needs a vector sign to be correct. Why does it need a vector sign? Because a change in direction also is an acceleration. If you have a constant speed but are changing direction, you're accelerating. So if you're driving your car, anything that changes the velocity, the speed or direction, is accelerate. So what things will accelerate your car? You have 3 accelerators on the car. Okay, the gas pedal, the brake pedal, the steering wheel. All of those accelerate the car. We call the gas pedal the accelerator. That's speeding you up. It's changing your velocity to make the speed faster. The brake pedal is slowing you down, changing the velocity to make you go slower. Sometimes that's called a deceleration. I actually try to avoid the term deceleration because deceleration simply means acceleration in the direction opposite to velocity. So in these pictures over here, you can see, oh, come on. Okay, I actually know what I did wrong. If I come down here, click on that, that was supposed to have worked. Okay, well there. If we look at these pictures, the first picture shows a green arrow for velocity. The velocity is going forward. It shows a purple arrow for acceleration. The acceleration is forward. What's happening to the speed if the acceleration is the same direction as the velocity? Speeding up. Okay, the second one has the acceleration opposite to the velocity. What's happening to the speed now? Slowing down. If we go down, the car's just turned around. It's traveling forward, but its forward is to the left. We usually call that negative in physics. We say it has a negative velocity because it's going to the left. The acceleration is to the right. We'd say it's a positive acceleration, but it's a deceleration because the acceleration is opposite to the velocity. And so is it going to speed up or slow down? Slow down. Okay. And of course, the last one's going to speed up. Nice job. Now, I can always change like that. Okay, so just one problem before I pass it off to the students. I said just one. I have more, but I don't have time for more. If I have an object that starts at a speed of 0, ends at a speed of, now I said a speed because there's no vector sign. But actually in the one-dimensional motion here, right, it's just left and right, The minus is actually giving us the direction. Because speed actually is scalar, it's always 0 or positive. You don't have a negative speed. If you have a negative, it's actually giving you a direction because of the negative sign, so it's a vector. So it's actually velocity final is minus 15 meters per second, with minus 15 meters per second meaning that it's going in the west direction. And it takes 3.00 seconds for this change to occur. I want to find what the acceleration is. I'm simply going to apply that equation. The acceleration vector is equal to the change in velocity vector over the change in time. So that's going to be the velocity final vector minus the velocity initial vector all over the change in time. Now, let me point out 0, it has v subscript 0 for the initial velocity. I put v subscript I. There is no meaningful difference between those. It's just I for initial or 0 for at time 0. And I always say ought for that little 0. I am pretty sure I read up and it was correct, but far more common to say not for that little 0. So it'd be v naught. I learned to say v ought for whatever reason. So I just need to calculate. Remember, delta is always final minus initial, so I just put in my final minus 15.0 meters per second minus my initial over my time 3.00 seconds. Sorry, I ran out of space. We can do this math in our heads, but I want to point out something. That 0, we're going to assume that 0 means at rest, so infinite significant digits essentially for that 0. If you have a cardinal number like, 1, 2, 3, I'm trying to think of things that would have. How many steps are in the staircase? 3 steps. That's an exact number. It has infinite significant digits. So sometimes you have cardinal numbers with infinite significant digits, and that's what we take the 0 as here. So minus 15.0 minus 0 is minus 15.0 still. Divide that by 3.00. How many significant digits will I have in my answer? With the multiplication division, you take the smaller the number of significant digits in each number. So the top had 3, 150. The bottom had 3, 300. And so my answer is going to have 3 as well. And of course, 15 divided by 3 is 5. So the correct answer is acceleration is minus 5.00 meters per second squared. Now, before I hand the problem over to you guys, those units, and I'll answer your question too, Alan. Those units, meters per second squared. How did I get that? I divided meters per second by seconds. Sometimes we write that as meters per second. But if you write a fraction with 2 divisor lines, it's a little confusing and somewhat ambiguous because one of them's a big divisor and one's a little divisor. Depending on which one you make the big divisor, you actually have different units. Meters per second squared is not a physical thing. You can't say, a second squared is this. Like, there is no such thing as a second squared. But it means meter per second change every second. So I am so used to it, I just don't blink an eye at it. But it's something you kind of have to get used to. Those units may contain things that aren't physical. Kilogram squared, once again, there's no such thing as a kilogram squared. Emily, what was your question?
So you're saying that the 0, since it's usually not or whatever, that's not a significant figure. So
I was talking about this 0. I'm saying this 0 is going to be considered infinite significant digits. We're going to say it's exactly at rest.
okay, so like that's not counted when we talk about multiplication division. So that's why it's 15.0 and 3.00.
Yeah.
So it's 3. Okay.
All right. Now let's we'll talk about graphical analysis is our topic for Monday, so I can skip over that easily enough. And I had this problem, but I'm going to go to a different one. The space shuttle problem. Here's the problem I'm going to have you work on as a group. What's the average acceleration of the space shuttle? And we have 2 periods, so I want you to find 2 average accelerations. the average acceleration in the first 100 seconds, and then going from 100 seconds to 500 seconds. And take these numbers as having 3 significant digits. So I'll just put a decimal point here and a decimal point here. So you have no significant issues. So work with your team to find those 2 answers. Remember, when your table has both answers, raise your hand. Okay, so we have a group that has completed it. So it's the one that started the class period. They're going to go for both. So come on up, and we'll go back to the page that you were working on before for you to do more work. So I wrote down the numbers in case you didn't have them written down. So they are going to now show us.
It's good to start off with the equation. So start off with
This.
oh, it's this one. Yeah, just start off with this one.
Final velocity minus initial velocity.
So it's
Well, you know.
Oh, okay.
That
Is
is
equal to
average is equal to.
the
I don't know how it
okay. Do we explain it while we write it down?
Yeah.
Okay. So then.
You can have one person talk, one person write.
Awesome. So the first acceleration is from time 0 to time 100 seconds, and the change in velocity is 1,026 meters per second. So the numbers, so plugging that into this equation, the average acceleration for the first period of time was that minus 0. Oh,
And yeah, assuming that the initial velocity was 0.
And so that's our first average acceleration, which was 10.3 meters per second
They got
squared.
the right significant digits, which is good.
And then to get the second acceleration, average acceleration, you do velocity 2 minus velocity 1 divided by time 2 minus time 1. And so that's what he's writing down right now. Which is 15.8 meters per second squared.
Okay, anyone have questions about how they did that?
And my hair rings off.
Straightforward? Did anyone else besides the table forget that
Yeah.
you raise your hand and get that extra credit chance? Remember to do that so you can get some extra credit. All right, thank you. You choose. You 3.
Oh, I'm not used to writing. I thought it was like the whole process.
Okay, to finish things off, let's look at the space shuttle. Oh, come on. So this is information that came from, this is actually a little worksheet that NASA's put together for this particular purpose. So if you go look at that, that PDF document, it's kind of cool. Notice the peak acceleration is capped at 29.4 meters per second squared. Why would they cap the peak acceleration? They want to get that baby out of here, right? They don't want to die. We say, James?
The astronaut doesn't die.
Yeah. The human body actually, the highest G force, as they call it, that the human body has survived as far as measurements in the laboratory setting is somewhere like around 9 or 10 Gs, which is pretty incredible. That is, a G is an acceleration of 9.8 meters per second squared. So 10 Gs would be 98 meters per second squared. And yeah, that's really pushing it. It was actually 2003, I went and visited the Houston Space Center, and they have a little centrifuge for people. And they put you in there and they spin you up to like 3 or 4 Gs. This here is 3 Gs. And by the time it got to 3 Gs, I was having a hard time breathing because my throat was starting to collapse. You know, it was like, ugh. Just having a hard time getting air through my throat. And so I was like really glad that we're not doing 10 Gs there. It was kind of cool just to know how hard it is. And it's not like somebody's hitting you with a baseball bat and you get that, 10 Gs right to the noggin all in one instant. And it's a little more comfortable than that. So they want to keep it so it's safe for the astronauts. So they're not too much stress on their bodies. Now, let's say that you're a fighter pilot. What branch of the military is your dad in, Michael?
He's in the Army.
He's in the Army. Okay, so definitely not a fighter. Well, actually, they do have aviators, but fighter pilots will pull maneuvers with really high G forces. They put really large accelerations on their body, which is tough. And a normal person would pass out. And so they have things like their G suit, something that has like fluid that will, when there's a lot of acceleration, it will respond to the acceleration, compress like their legs and push blood out of there so they can keep some blood going to their brain so they don't black out. They still do black out sometimes. So good reason to keep that capped. Now here is the actual data for a space shuttle launch. And so I plotted, in physics we use graphs a lot because you can look at this graph and you can get exactly the feel for what's going on with the data. This data table is good. You can read through and get a lot of information, but it's quicker and easier to look at the graph. So looking at the graph, the first thing you note is the altitude graph is not what you expect. What do you expect the space shuttle's altitude to do? To keep going up, right? If you look, it actually reaches a maximum here and then comes back down, but it's not outside of orbit yet. And you're like, well, you should be like, what in the world? what they're doing is when the space shuttle takes off, the Earth, of course, is rotating. And so it takes off and then it goes over on its back and starts going the same direction the Earth is rotating. Can anybody think of a reason why they would go the same direction the Earth is rotating?
Is that to reduce the G-force? Or is it just also to get into the rotation?
Reduce drag.
It's kind of what James said for his second part. The Earth is rotating, so the Earth is, the sun rises in the east. That's because we're rotating toward the east. So here's the Earth. It's going to take off and rotate with the Earth toward the east because the Earth's air is rotating with the air. And so the speed that we're measuring is the speed relative to the Earth or relative to the air. And if it's rotating with the Earth, it's going faster and faster. And so it's energy is the important thing here. It's picking up energy from the Earth's rotation. So you can put it, so you're accelerating this way, not having to go against gravity, but still gaining speed that's going to help you escape. So that's why they do it. And that's why the elevation kind of levels out, because now they're just going the same direction, keeping roughly constant altitude and speeding up. And then that speed is going to allow them to escape. Also up here, there's basically no atmosphere anymore. There's no resistance. If you look at the speed graph, and here's where I have to do this correctly. If you look at the speed graph, you notice that it has, okay, I can't draw when it's zoomed in. That I know. The speed is increasing and then it slows down and it's increased. Well, what do we call the rate at which speed is changing? Acceleration. So this line getting steeper, the speed divided by time is the slope of a line, but speed divided by time is acceleration. So the slope is the acceleration. And you can see it's accelerating up there until about 100 seconds, and then the acceleration slows down a bit. And then it picks up again at the end here. The reason is because it has two different rockets. It has the rocket that it takes off with for the first 100 seconds, then it jettisons that, fires up the second set of rockets, and I think it jettisons them at that point, and continues accelerating again.